Welcome everyone to a new virtual seminar Geometry with Symmetries. Today it's my great pleasure to introduce Matt Langford from ANU in Australia, and he's gonna be speaking on ancient solutions with small symmetry groups. So go for it, Matt.
Thanks, Ramiro, for the introduction and the invitation. It's an honor to be part of this seminar. So I'm going to speak about ancient solutions to geometric flows with small symmetry groups, and I'll talk about a number of constructions which involve exploiting symmetry to greater or lesser degrees to construct interesting and very useful, sometimes very useful solutions to such equations. So the model for all of these, well, at least in the parabolic case, the model for these equations is the classical heat equation. I'm sure you're all very familiar with it, but let me just tell a little story that helps give some context on what we'll be doing. So consider a function u, which is just a function of a space variable in R3x and a time variable t. And suppose that this function satisfies this equation, ddt of u is equal to the Laplacian of u. Well, according to Fourier, in his treatise on heat, the value of u at the point x and t models the temperature of an infinite universe at the point x in space at time t. Now, in our model here, the heat has been evolving by this equation since the beginning of time, which is infinitely long ago. And the heat equation is a diffusive process. So we've got this temperature function undergoing a process of diffusion in which regions of relatively high temperature flow towards, or energy flows away from such regions towards regions of relatively low temperature. But in our model here, this mixing process has been going on for an infinite amount of time. So at any given point in space and any time, this process has been going on for an infinite length of time. So it's natural to expect that, in fact, in this model, we should just get something very boring in which the temperature is constant. But of course, this is not necessarily true. There are many non-trivial solutions to this equation. So here's two. For example, mod x squared plus 6t, very easy to see that this satisfies the heat equation. We can all do that in our heads. And similarly, e to the t cosh of any of the space variables. So our conjecture turns out to be false. And I should just say, feel free to interrupt during the talk if you have any questions as well. So yeah, don't be shy. Okay, so the conjecture is false, but of course, when our conjectures are false, we just add some additional hypotheses until they turn out to be true. And in the case of the heat equation, we have the following, probably not as well known as it should be, theorem, which I'll refer to as Appel's theorem, but the statement given here is due to Hirschman. And that says that if we have such a solution to the heat equation, so defined on all of Rn and defined for all t, if that solution is both positive and satisfies this sub-exponential growth spatial growth bound, then yes, indeed, we recover the conjecture that u should be constant. Okay, note, well, this should, so even if you're not familiar with this particular theorem, this should remind you of the Liouville theorem, the classical Liouville theorem, which says that any bounded, well, in fact, any non-negative entire harmonic function is constant. Okay, so this is very, very similar, except, well, here we have, instead of an entire harmonic function, we have a solution to the heat equation on all of Rn and with an infinite history. And instead of just having a positive solution, we have this exponential growth in space bound. So we have this additional bound. Well, maybe we can relax that. Well, of course, we can't due to the examples given here. So the first example is neither bounded above or below. The second example is bounded below, but it has an exponential growth in space. So both of these conditions are actually sharp. So this really is the parabolic version of Liouville's theorem. Okay, and in fact, so just as for elliptic equations, so-called ancient solutions to parabolic equations, so instead of an entire solution for an elliptic equation, we have a solution to a parabolic equation with an infinite history. We call such things ancient solutions. So these are the parabolic analog of sort of entire solutions to elliptic equations. And just like in the elliptic case, this kind of rigidity is sort of a hallmark of such solutions. Okay, so here we've assumed an eternal solution, not just an ancient solution, but of course, for the heat equation, there's no loss in generality. We always have long time existence. But in general, for nonlinear parabolic equations, you may only have finite future existence. So we'll really be looking at ancient solutions. Okay, so that's the model theorem. So for heat equations, ancient solutions satisfying some kind of positivity and perhaps growth condition should be quite rigid. So that's the model. I'll be interested in geometric flow equations, such as the Ricci flow or the mean curvature flow, or even other kinds of flows. And for these equations, well, these equations are nonlinear equations. They are parabolic in a certain sense. They're nonlinear in a certain sense. And in contrast to the heat equation, nonlinear parabolic equations do suffer singularities in finite time. Under suitable structure conditions for your flow equation, for example, mean curvature flow, Ricci flow certainly satisfy this. You have parabolic regularity theory, which guarantees that singularities are characterized by curvature blow-up. Okay, so the only way the solution can fail to exist forever is that you have curvature blow-up, and this is actually typical. Okay, so in the compact setting, this will always occur in mean curvature flow, and in positive curvature, it'll always occur in Ricci flow. So the canonical examples are shrinking spheres, say for mean curvature flow or Ricci flow. Okay, so you have these singularities for these nonlinear equations, and the ancient solutions, which we've just looked at, play really a fundamental role in understanding singularity formation. So why is that? Well, if our flow admits some kind of a scale invariance, so for the heat equation, if you scale your function of scale space by lambda squared and time by lambda, you get back a solution to the heat equation. Similarly, for the mean curvature flow or Ricci flow, you have this kind of parabolic scale invariance. Well, then the game you can play now is that if you have a sequence of points suffering a singularity where your curvature is blowing up, well, you just sort of zoom in space and dilate time, and you still get a solution to the equation, but you're sort of making it better. You're smoothing out this curvature singularity, and in the limit, well, you hope to obtain a limit of this procedure, and because you're scaling time infinitely much, you end up with, well, in space infinitely much, you end up with a complete ancient solution. Okay, so our complete ancient solutions, if we understand them very well, then we should have a good understanding of singularity formation. So here's just a little picture of what might happen. You have this little neck in this non-positively curved sphere. So this has sort of positive curvature in this little neck region. So it's trying to shrink down and cause a curvature singularity. At the same time, you have this little tip to the right is trying to, catch up and sneak through this neck as it shrinks down. It sort of gets caught in the middle, but as you sort of perform a sequence of rescalings, you end up with this steady ancient solution in the limit. That's just the heuristic. I'm sure you're all familiar with this procedure. But a crucial, so this is really, really useful for the following reason. Well, our geometric flow equations tend to quote unquote pinch curvature towards the positive. Okay, so we expect when we do this argument, we don't just get an ancient solution, but we get a solution which has some kind of positive curvature condition. Okay, so when we do this blow up argument, we expect not just to see ancient solutions, but positively curved ones. These are of particular interest. And as we expect from from Appel's theorem, it's precisely these positively curved solutions which should admit rigidity properties. Okay, so this is a very, very nice situation to be in. You know, we get positive curvature, and it's precisely these solutions which we should expect to have some kind of a class or hope to have some kind of a classification. Okay, in some cases, you can also expect that the limit has some kind of a self-similarity property. I'll be most interested in the steady or translating case today. Okay, if you need more motivation, which I'm sure this audience probably doesn't, classifying the singularity models, this is crucial in sort of applications for these flow equations, which require some kind of long time existence and convergence. And the most famous example is, of course, Perelman's proof of Poincare conjecture, which really kicked off this this field of trying to understand your singularity models and your ancient solutions. Okay, so understanding them is really crucial for applications of your flow. Okay, so let me talk now about how to construct such examples. Okay, so our ancient solutions model singularities. Well, do we have any ancient solutions for our flow equations? Well, the most basic one. I apologize.
There's just a typo in simple ODE there.
Yes.
No worries.
Oh, typo. Yes, there's two typos actually. It should say simple, and R should be a function of T, not R. So the most basic example of a solution to these flows turns out to be also an ancient solution, are the shrinking spheres. And in order to construct them, you just assume that your solution has spherical symmetry, and then the nonlinear parabolic equation just becomes an ODE for the radius of the sphere. So that's a couple of typos there. Thanks, Owen. And so it's just solved very easily, and you get these spherical solutions. And in fact, you see from the ODE that these become ancient solutions. So this is true for Ricci flow and mean curvature flow and many others. So you impose maximal symmetry, and you get this solution very easily. You can also just look at the equations in low dimensions. So if you look for steady or shrinking solutions, well, this reduces your parabolic equation to an elliptic one, and then if you go down to one dimension or low enough dimensions, this elliptic equation it becomes basically an ODE. So that's for the mean curvature flow. You can easily solve this ODE to get the Grim Reaper translating soliton, or the analog for Ricci flow is, of course, the cigar soliton. So here, low dimensions and sort of the soliton hypothesis. So moving under a symmetry group of the equation, plus low dimensions makes it a simple ODE. Slightly less trivially, so in higher dimensions, you can make the soliton hypothesis. So that makes an elliptic equation, and you can reduce it to an ODE by now imposing a sort of maximal symmetry, well, almost maximal symmetry hypothesis. So once you have this elliptic equation, you impose axial symmetry. It reduces the ODE, reduces the elliptic equation to an ODE, which you can then solve by ODE methods. But this is slightly more difficult now, because in order to get a sort of complete solution to the equation, this ODE has to satisfy a singular condition at the axis of symmetry. So less trivial now to actually make that work, but not too difficult. There's various approaches. Okay, you can look at, instead of translating solutions, shrinking solutions. So, and there's this classic example of Anganon, which looks for a torus. Well, not a torus, an axially symmetric donut solution, self-shrinking solution to mean curvature flow, and then this reduces it again reduces the elliptic equation for self-shrinkers to an ODE for the profile curve. But now you have this difficult, so you can always solve this ODE locally, but you need to make sure it closes up to give you a closed profile curve. So, okay, reducing to ODE doesn't completely solve the problem. You do need to do some work now to get your solution. There's another, well, these other one-dimensional solutions to curve shortening flow, or this two-dimensional King-Rosenau sausage solution for Ricci flow, can be obtained by imposing a separation of variables Ansatz. So for the curve shortening flow, you can look at the time of arrival function. So this is a function on the plane which gives you the time at which the curve reaches that point in the plane. This function satisfies a partial differential equation, elliptic equation in two variables, and if you make this separation of variables Ansatz, you again reduce it to an ODE, which has these interesting solutions. You can do a similar sort of separation of variables in the Ricci flow to get this so-called sausage model. And there are many further constructions which sort of follow the same philosophy, although often much more involved, imposing much more complicated symmetries. But the idea is it's the same philosophy. So you impose some kind of clever symmetry or separation of variables Ansatz, and then use the algebra to reduce the partial differential equation to some kind of ODE system, sometimes very complicated ODE system, and then analysis of this ODE system gives you examples. And there are many results in that direction. Okay. But I'm going to go in a slightly different direction today. So let's leave symmetries for a moment and just generally discuss how you might go about constructing non-compact solutions to elliptic and parabolic equations. And note that for these flow equations, even if we want a solution with compact time slice, constructing an ancient solution is a non-compactness condition. Okay. A sort of standard classical approach to solving a non-compact problem is to solve a sequence of approximating compact problems and take the limit. So the compact problems can usually be solved by standard methods, but then you want to approximate your non-compact problem by these compact ones and take the limit. That's just the basic idea. And the first such construction for ancient solution to geometric flows that I'm aware of is Perelman's examples, and this is a very nice idea. So let me just recall what Perelman constructed. He constructed these O1 cross O3 invariant ancient Ricci flows on the 3-sphere, which decomposes into two Bryant steady solitons connected by a shrinking cylinder. So something like this. So it looks at the left and right sort of tip regions like two steady steady Ricci solitons, the Bryant solitons. And in the middle, you have this shrinking cylinder-like region, okay? But this argument is extremely robust. Analogous constructions have since been carried out in higher dimensions by Tim. For more general bisymmetries, I think I can give Hasselhofer credit for that. For mean curvature flow as well, essentially the same construction gives you examples for mean curvature flow. And also it actually becomes quite a bit more difficult, but you can do it for a very large class of fully nonlinear extrinsic geometric flows as well. So very robust construction, very clever idea. Let me outline roughly how it goes. Okay, so you start off with a unit radius cylinder of length 2j. So for any j, at least 3, say, and then you cap it off with spherical caps. Okay, you do this smoothly just to make everything work a bit more nicely. Under the flow, so you take this as your initial condition and you flow it by, say, mean curvature flow. You can do this in the Ricci flow. The construction is very similar, but I'm just going to focus on, say, mean curvature flow. This solution will actually collapse to a point after time approximately 1. So it'll collapse to a point and it will become asymptotically round as it does so, according to Huysken's theorem, which is the mean curvature flow analog of the Hamilton-Böhm-Wilking theorem. It does this after a time approximately 1 because the original cylinder, the infinite cylinder of radius 1, is an outer barrier, and this collapses in time 1. After time translation, so we translate by time approximately 1 to make the final time 0. And now what we can do is use inner barriers, use shrinking spheres contained on the inside to prevent the, basically to control the eccentricity. So these shrinking sphere inner barriers guarantee that the apogee and the perigee only, so the maximal distance and the sort of minimum distance axis, or the radius of the rotation axis, decrease by a factor of, so you have a controlled amount of time after which they decrease by a factor of half. And using this property, you do like a parabolic rescaling, and you can arrange the following. So you can arrange that so at time t equals -1, you can arrange that the eccentricity is bounded away from 1, say 2, while the in radius is still approximately 1/2. Okay, and when you do this, the initial times get pushed back to t equals -infinity. And so now you're basically in gravy. So the initial conditions are uniformly non-collapsed. So this gives you non-collapsing estimates, which are well known to give you sort of regularity estimates. The non-collapsing is uniform in J. So these estimates in CK are uniform in J, and then you can just take a limit using a suitable version of the Yatzila-Ascoli theorem. Okay, and because the initial times are going off to -infinity, you get an ancient solution. Because of the construction at time t equals -1, the eccentricity is 2, so you're certainly not getting something you already knew, like the shrinking sphere. So this is the idea, and really making this precise is not much more difficult. Okay. And so you can do this. If you do this in an explicitly symmetric way, bisymmetric way, then the resulting solution you get is bisymmetric. But if you try to do this in an asymmetric way, there's actually no guarantee that the solution you get isn't symmetric unless you have some kind of control. So that's worth pointing out as well. And indeed, there are some uniqueness conditions under uniqueness of these symmetric solutions. So in some cases, you cannot prevent the limit from actually becoming symmetric. Okay, so that's Perelman's basic idea. This sort of works really, really quickly and elegantly. One reason that this works so well is because you can do this parabolic rescaling and you have these non-collapsing estimates. Okay, so I want to talk about a couple of constructions now, which are quite a bit more difficult because you don't have this parabolic rescaling or these non-collapsing estimates available. But it's still the same philosophy. Okay. So the first theorem I want to mention is this so-called pancake construction. So following examples, solutions to mean curvature flow were conjectured by Daskalopoulos, and we're able to construct them very precisely with Theodora Borni and Giuseppe Tinaglia. And so we constructed these solutions which have this bisymmetry, O1 cross ON symmetry, and the following properties. So these are closed convex solutions. So Huysken's theorem guarantees that they shrink to a point at the final time, which we can take to be 0, a round point. Now, as t goes to -infinity, the time slices of this solution are actually bounded by 2 parallel hyperplanes, and the solution converges to these 2 parallel hyperplanes locally uniformly. And if we look at the region, the sort of edge region of maximal distance, then what we see is Grim Reaper translating solutions forming in this region. So let me just give you a picture. So as time moves forward, these time slices shrink down, becoming rounder and rounder as they collapse in a point. But as t goes backwards to -infinity, you look around this edge region, well, it starts splitting off a hyperplane, and then the profile curve starts looking more and more like a Grim Reaper solution. So that's basically what they look. The picture gives a much better description than the words. Okay, so I'm just going to quickly describe how you go about constructing these solutions. And again, the construction is sort of follows this philosophy of taking a limit of solutions to compact problems. Okay. So the first thing, which turns out to be actually quite important, is to choose a sequence of initial conditions which are a good approximation to the desired ancient solution. So what you want to do is you want to take a sequence of surfaces which look like these time slices that you want to construct, and then you're going to flow these given time slices by mean curvature flow. Okay, so you take a sequence of initial conditions which are a good approximation to the ancient solution you want, and what we do is we just take the one-dimensional example, which is this Angular oval solution, and then you take a very, very early time slice of this Angular oval solution, and then you just rotate it. You add an ON symmetry. You rotate it about its axis of reflection symmetry. Okay, so maybe going back to the picture, you see these profile curves, these oval-like curves. So in the construction, you would take these profile curves of the ON symmetry to be some very, very early time slice of this one-dimensional solution. Okay. So of course, rotating this one-dimensional solution doesn't give you a solution to the mean curvature flow because you've added this rotational curvature. But it should be approximately, the philosophy is that it should be sort of somewhat close to one. Okay. So then what you do is you just evolve this sequence of initial conditions by the mean curvature flow. By Husken's theorem, these solutions contract to the origin, becoming round after some time tj. And then we just time translate so that the final time is t equals 0. Okay, and so now our task is to show that the time taken for this to happen becomes longer and longer and longer. And then we need to get some kind of uniform estimates for the regularity in order to apply our Taylor-Ascol. So that's the game that you now need to play. Okay, and the sort of key to making this all work, the key estimate goes as follows. So basically, the profile curves, because for these very, very early times, the rotational curvatures you get from the ON symmetry are actually quite small and well controlled. The profile curves approximately satisfy curve shortening flow. So you have so you analyze these profile curves with the rotational symmetry. They approximately satisfy curve shortening flow. But curve shortening flow has this really important property that's extremely useful. It says that the enclosed area decreases at a fixed rate. Okay, and so what we get for our solution for these profile curves, we get that the area decreases at a fixed rate plus some small error term. Okay, independent of the sequence j. That's the key point. So this is what gives us some kind of uniform in j estimate, and this rotational symmetry really allows us to use special properties of the flow in low dimensions. Okay, so in particular, it's clear that, well, because the initial profile curve is the profile of a solution to curve shortening flow, the enclosed area is exactly 2 pi t at the initial time, or 2 pi j rather at the initial time. So because this error is small, you find that the time taken for the area to decrease to 0 is approximately equal to j. It's not exactly, there's some small error, but it's approximately j. It certainly goes to infinity as j goes to infinity. Okay, so if we have some regularity estimates and we can take a limit, we now know that our limit will be an ancient solution. So the key now, the game now, is to obtain some uniform in j regularity estimates. Notice that we can't perform Perelman's rescaling argument because our solutions are, so the width of our solutions is fixed, so we don't want to ruin that width by rescaling, and the initial conditions are no longer uniformly non-collapsed. So the initial conditions are actually, the collapsing is degenerating as j goes to infinity, so we can't use any non-collapsing estimates either. So the trick now is to use, we use the fact that the area enclosed by the profile curves, because our profile curve is confined to a strip, is actually comparable to the diameter. Okay, so, and we've got a uniform control on the enclosed area. This gives us uniform in j control on the diameter. And I don't have time to go into it, but we can use a barrier and maximum principal type argument to get control on curvature from diameter control. Okay, so we've got uniform control on area, uniform in J gives you uniform in J control on diameter, which now by this barrier argument gives you uniform in J control on curvature. And now we're happy because parabolic regularity then gives you control in CK for all K uniformly in J. So now we're in gravy, we can just apply some version of Arzelà-Ascoli to obtain a limit. And because the limit lies in this slab region, there's no, and we have control on the diameter, we get some non-spherical limit, and a little bit more work will give you the asymptotics. So the key thing that we can bootstrap from here is that the profile curves satisfy curve shortening flow plus small error. So we've reduced, so we haven't quite reduced the problem to an ODE analysis, but we've reduced it essentially to a one space dimensional parabolic problem. This construction also turns out to be very robust, with quite a significant bit of extra work with Theodora, Tim, and Ramiro. We were able to make this construction work in the context of Ricci flow. So you can construct sort of analogs of these examples in the Ricci flow as well. And also with a certain amount of extra effort, with my PhD students, Satya Rangaswamy, we're able to construct such examples in a sort of large and very natural class of fully nonlinear extrinsic geometric flows. Okay. So yeah, so the philosophy here is that your symmetry ansatz, now it doesn't quite reduce you to an ODE analysis, but it reduces you to a parabolic equation in one space variable, and these equations have really useful extra properties that can be exploited now, which cannot necessarily be exploited in higher dimensions in general. Okay, so that's the ancient pancake solutions. So now let me talk about a somewhat analogous construction of steady solitons. So these are called the flying wings. So that name is due to Hamilton. So he conjectured that such solutions should exist. So the following solutions should exist for Ricci and mean curvature flows. And so the idea is that, again, you have some slab region between two parallel hyperplanes in which you have these steady solitons. Well, let me give you a picture in a second. And the way we construct them is by imposing some sort of the strongest possible symmetry ansatz, given that we're confined to a slab region. And the solutions we construct look like two grim hyperplanes of tilted angle defined by the width of the slab. So maybe just let me give you a picture to show you what I mean. So you have this vertical slab region in which the surface on the left, it lies in between. It translates upwards with constant speed under mean curvature flow. And at infinity, it sort of looks like, well, in either direction, at infinity, it looks like a hyperplane cross a grim reaper, but tilted, okay? And the tilting angle of these two grim hyperplanes is actually completely determined by the width of the strip in which you lie, or vice versa. Okay, so you have a very good description of these solutions, and you have one for every width. And the picture on the left is a picture of this Northrop Grumman flying wing aircraft, which was the inspiration for Hamilton's nomenclature. Okay, so that's basically how they look. I should also add that Yi Lai has constructed the Ricci flow analogs of these solutions by a quite a different method than ours, actually. So a very interesting method. But I won't talk about that. I'll just give you our construction for mean curvature flow. Okay, so we want to play the same game. So we've got now, well, instead of a parabolic problem, we've got this elliptic problem of constructing these steady solitons. But these solutions are non-compact. And so the idea is to find a sequence of compact problems which approximate our non-compact one, and then try to take a look. So the first step is what we do is construct a sub-solution. So we seek a sub-solution to the equation, which is a good approximation to the desired solution. And what we do is we sort of look for a sub-solution which has the desired tilted grim reaper asymptotics. Okay, and maybe somewhat fortunately, the first thing we tried works. So we use a sort of anisotropic. Well, the first thing, not quite the first thing. So we look at the arrival time of the ancient pancake solution of one dimension lower. So this doesn't quite work because the asymptotics aren't quite right. So we do an anisotropic scaling of this object to force the asymptotics to be good. Okay, and it turns out that this does give us a sub-solution. Okay, so this is a graphical object, and it gives us a sub-solution to the corresponding elliptic graphical PDE. And now what you do is you take this sub-solution sigma. Now, if you translate it down,
Matt, can I interrupt you?
Of course.
What's the picture? So you have the pancake, right? So are you making the pancake sort of? Are you bending it to make an angle somehow?
Not. It's sort of already.
And you don't.
So if you look at this graph on the left, if this is now our sub-solution instead of the solution, the level sets of this object are the pancakes. So it's the arrival time, which means that its level sets are the surfaces which evolve by mean curvature. And so since I can't draw 3 dimensions, so in this case, the level sets are the Anguinant ovals. But in higher dimensions, you add this extra axial symmetry, and then the level sets are the pancakes.
All right.
Yeah. It would actually be upside down if it's the arrival time, but so you change it by a sign. And as I said, this doesn't quite work because you get asymptotics which sort of look like this, but you have to do this anisotropic scaling to make the asymptotics exactly what you want. Okay, all so right. I hope that clears that up. Okay, and luckily it turns out to be a sub-solution. And in fact, I'm lying a bit. We don't actually use the pancakes because we don't have a precise description of them. We actually use those approximating solutions to the pancakes, these rotated Anguinant oval things. Okay, and so you have a very precise description of them, fairly simple functions, and you can compute the operators, and you get that they're a sub-solution. It's a nice little calculation. Okay, so you've got this sub-solution, and now if you translate this function downwards, it's still a sub-solution. The equation's invariant under vertical translations, and so you translate down by say j, and then you look at the zero set, or the zero sub-level set, and this gives you a domain. So you take the zero, should be the sub-zero, or the zero sub-level set. This gives you now a compact domain on which you can try to solve the Dirichlet problem for the translator equation. Okay, and by classical PDE theory, you can do this as long as you have suitable barriers. So if you have an upper and lower barriers which attain the zero Dirichlet boundary data, then elliptic theory gives you what you want. And we've got a sub-solution by definition. This is the zero set of our sub-solution. So it attains the boundary data. And it turns out fairly easily, it's very easy to see that the zero function is actually a super solution. So now you have upper and lower bounds which give you a priori estimates for height, and boundary gradient maximum principal range gives you interior gradient estimates. It's all quite standard. So once you have upper and lower barriers which attain the Dirichlet boundary data, elliptic theory gives you estimates in CK alpha for any alpha, and then method of continuity gives you a solution to the Dirichlet problems for these compact problems. Okay, so for each j, we've got these domains omega j, which approximate our strip region on which we're trying to solve the equation. And we've got this sequence of solutions to the Dirichlet problem. Of course, by uniqueness of solutions, these solutions inherit the implicit symmetry of the domains here, the O1 cross On minus 1 symmetry. Okay, so first step, we've solved this sequence of compact problems. Now we want to try and take a limit. So two things we need to do. We need uniform estimates. So the estimates we got from the barriers depend on, of course, on J. So we want uniform in J estimates. And the idea, which is really clever idea of Theodore and Giuseppe, is to use the theory that already exists for minimal hypersurfaces. Okay, so for minimal hypersurface, you have this wonderful theory, which due to Allard, Almgren, etc., in which you sort of want to prove curvature estimates. Curvature estimates by elliptic theory give you estimates in CK for all K. And what you do is if you assume that you don't have curvature estimates, and then you perform a scaling argument. You now blow up about a sequence of solutions at which you don't have these estimates. And because you're blowing up, just like in our parabolic case, we saw ancient solutions in the limit. Well, in the minimal surface case, you see a minimal cone in the limit. And then the idea is to show that, well, the only minimal cones are the flat planes. But if you have a flat plane, you have this regularity, this regularity theorem of Allard, which says that, well, in fact, you do have estimates after all, which is a contradiction. Okay. Why can we apply this idea for the translator equation? Well, the translator equation says that the normal component of the vertical velocity, which is just the unit vertical vector, is equal to the mean curvature. So the mean curvature by the equation is just bounded by 1. So when you do a rescaling argument, you do get a minimal cone in the limit. Okay, so essentially the translator equation is minimal surface equation plus bounded lower order terms. So doing this blow up argument actually allows you to apply the minimal surface techniques. And that's the idea. So you use the standard minimal surface blow up argument to get uniform. Well, you get a priori estimates in CK, which depend only on the regularity of the boundary data. But the regularity of our boundary is completely uniformly controlled. There's only one problem, and that's that these minimal surface arguments only work in low dimensions because there do exist minimizing minimal cones in high dimensions, in dimensions at least R8. So 7-dimensional minimal. There's this Simon's cone in R8, which is a minimizing minimal cone, but in low dimensions, these don't exist and the argument works. For us, we can get around this by the symmetry hypothesis. So essentially our O1 cross O1 n-1 symmetry hypothesis reduces us essentially down to the 2-dimensional case, in which case you don't have these counterexamples. So that's one way in which this symmetry helps us in this case. So hopefully that explanation was helpful if you're not familiar with these ideas. There's one more thing you need to do though, just as in the ancient solution, the ancient pancake case, and for Perelman solutions, you need to show that the sequence of initial times is going back to minus infinity, or you don't get an ancient solution. Well, for the translators, you need to show that the heights are converging to infinity, or you don't get a complete solution. Okay, and now you use in this case, you use a barrier argument. Turns out that the ancient pancake, this totally symmetric ancient solution to the mean curvature flow, gives you an upper barrier, and you can show that this upper barrier gives you lower height bounds, which do the job. So that's another place that this symmetry comes into play. So this symmetric. So okay, this is a good example of so you can use symmetry to construct special solutions, solutions which have a high degree of symmetries. But once you have these solutions, they can be extremely useful, for example, in these barrier constructions. Okay. Oh, and there's one more thing you need to do is you need to do a sort of more refined barrier argument using this ancient pancake to show that. So the other thing you need to do is show that when you take this limit, the width doesn't drop, because you want to show that you have solutions asymptotic to any slab of any given width. So you need it to perform a more refined barrier argument to show that the width of the limit doesn't drop down. Okay, so hopefully for the non-PDE audience that wasn't too unfamiliar. And so in the last 5 or 6 minutes, let me talk about this far more general construction, which gives rise to a very large class of examples. And it does follow the same kind of ideas, but requires much less symmetry. So the idea is as follows. Unless, feel free to ask any questions about the previous stuff, or I'll just continue with the final bit. So the idea now is to construct a large class of examples of compact and non-compact ancient solutions to the curve shortening flow. And again, these solutions are going to lie between two parallel hyperplanes. And so the idea is to construct a solution which, say, take this picture on the left. We've got this circumscribed polygon around the unit circle. And we're going to try to construct a solution which at time minus t for very large, well, at time t for very large negative times, okay, so you've got this region between two parallel planes. You look at the mid plane, say the z equals 0 plane, and when you take an intersection with the z equals 0 plane, the solution approximately looks like this. Circumscribes a circle of radius approximately t, or negative t, and at these edges, where the edge is tangent to this circle, you see something that looks very much like a grim plane. Okay, so you have some line, but then in the direction transverse to the slab, you get a grim reaper forming. And then where these edges form vertices, you see these flying wing solutions forming, at least for sufficiently negative t. So somehow at time negative infinity, you have these flying wing solutions which have some configuration like these vertices, and they have these common asymptotes, which are the edges, which connect in grim hyperplanes. So it's a bit hard to describe, but hopefully that was clear enough. So your solution at t equals minus infinity sort of decomposes into these flying wings, which have common asymptotes, forming these polygonal examples. Okay, and in order to construct them, well, you want to find initial conditions for the flow which approximate very early time slices of the solution you're trying to construct. And what we do is we just take this large circle and then take every edge on our prescribed polygon, and instead of having an edge, you take a grim plane. Okay, so you take the plane part, or a grim plane. So the linear part is just the edge, but then in the vertical direction, you have this grim reaper. Okay, so you take the intersection of the regions enclosed by all these grim planes, and that gives you a convex set. Okay, it's no longer smooth because you have singularities at the vertices and then the regions of intersection, but it's still a convex set. And so you can still flow that under mean curvature flow. There's really no problem in doing that. You have estimates which allow you to do that, the boundary of any convex set. So you evolve that by mean curvature flow, and then you want to prove some estimates. You want to prove that the time of existence is getting larger and larger, so that the solution you get when you take a limit is an ancient solution. So you need curvature estimates so that you can apply Artila-Ascoli to actually take a limit. But even in that case, once you've done that, you need further estimates to make sure that the limit you get isn't something you already know, such as the rotationally symmetric agent pancake. So yeah, you try to play the same game. You have a sequence of initial conditions which approximate what you want. You evolve them by mean curvature flow. You want to show that the time of existence before they shrink to a point is becoming larger and larger. And you want to obtain estimates for, say, curvature, so that you can apply Artila-Ascoli to take a limit to get an ancient solution. But then the real difficulty in this case is to show that the limit that you get isn't the maximally symmetric thing, the ancient pancake. So as I've said, the edges in these pictures correspond to grim planes at a distance t to the origin. Vertices where they intersect should be looking like these flying wings of the same exterior angle. And okay, the short version is that this construction works. It actually works in all dimensions as well, so long as you're the polytope with which you're doing this circumscribes the unit sphere. And in fact, we still can't quite make this work for all circumscribed polytopes. We need some additional conditions. Okay, so I'll talk about that in a second, but yeah, so we can actually do this in fairly high generality in all dimensions. We get a very large number of examples. So one situation where you get an example surely is for any simplex. So if there are only, say, 3 edges in the compact case here, or 2 edges in the non-compact case, then you always get a solution. In these higher dimensional versions of that as well for compact and non-compact simplices. And these need not be symmetric simplices. And the examples confirm a conjecture of Hamilton. Hamilton sort of had a rudimentary conjecture about how to glue these flying wings together to get solutions. And in fact, there's another conjecture of White, which says that certain non-compact examples of these guys shouldn't exist. So we were able to construct examples confirming Hamilton's conjecture and counter examples to White's conjecture. We also showed, so I'm only focusing on circumscribed polytopes here. We were also able to show using the ancient pancake in a very precise barrier argument that that's a necessary condition. So there are no ancient solutions of this form which do not, in a suitable sense, circumscribe the ancient pancake. And when n equals 2, so even though, for example, for the simplex case, you don't, so this polygon need not have any symmetries at all. We show that the solution you construct necessarily has, well, at least when n is equal to 2, it should be true in higher dimensions as well. The solution you construct has a reflection symmetry about the horizontal plane. So even though the intersection with the horizontal plane need not have any symmetries, the solution you get has a reflection symmetry about that horizontal plane. And yeah, as I said, so there we construct examples for which that is the maximum amount of symmetry you get. Okay, so symmetries aren't appearing very much here, but symmetries are crucial to the construction. So in some sense, the circumscription of the unit disk is a kind of symmetry ansatz. But we also use this rotationally symmetric example that we constructed earlier, like over and over and over again in barrier arguments. It's somehow the only tool we have in some sense, that plus the differential Harnack inequality. So we have to use this example that we've constructed over and over again in barrier arguments to control how these solutions form. But we still can't get all circumscribed polytopes. So let me maybe quickly describe what goes wrong. So let's say we want to construct an example which decomposes into the situation on the left here. Well, we can show that the solution we get has to circumscribe the unit disk. Okay, and we can also show that it has at least 3 vertices. Okay, but the problem is that we can't stop, say, this bottom right edge from, say, detaching and moving away. We can show that in the limit it has to touch the disk, but we can't rule it disappearing completely into a vertex. Okay, so we can show that each edge you get in the limit has to be tangent to the disk, but we can't prevent some edges from sort of moving off to infinity and disappearing at another vertex. So you would sort of reduce the number of edges you have in the construction, but the minimal number you can have is 3. So in general, so that's why the construction works for any simplex, or you can just impose a dihedral symmetry, which solves that problem as well. So this is sort of an artificial problem, we think. We conjecture that you should be able to do this in general, but yeah. And there's the conjectures. So you should be able to do this in general, and you should be able to do this for other flows. But I should stop there because I'm out of time.
Thanks, Matt. A very nice talk. Are there any questions or comments for the speaker? I actually wanted to ask 2 things. So first, I mean, the previous construction of the flying wings in mean curvature flow, right? So that uses in a very strong way this arrival time function. And I mean, which is something very extrinsic, so to speak. I'm just thinking,
Yeah.
do you think there's a way to adapt these ideas to the intrinsic setting, Ricci flow?
Do you mean for the
I know
flying wing?
yeah. No, well, I mean, in general, like what will be the analog of such a construction? Like, I mean, if you look at the flying wings, they don't look very natural, right? Until you say, well, the arrival time, they actually look like ovals, and then it feels much more natural when you look at them
Yeah.
from this point of view.
So I think our construction has a lot of things that are very special. For the regularity theory for minimal surfaces, the barrier construction, the pancake are very special. But this final construction actually gives you flying wings. So if you take the example on the right, but you just take two edges, so you take just a wedge, this will give you flying wings. And I think this construction has a lot of hope of working in Ricci flow. And this is actually a much easier construction of the flying wings for mean curvature. Well, in some sense, it's a much easier, more natural construction as well. Another thing that's really good about it is you automatically get convex solutions, but I didn't mention it. The construction we gave for the translators gives you at best graphical solutions, which are at best mean convex. You actually have to work harder to show that they're convex, whereas this construction here implicitly
you start
gives you
from
positive.
convex, yes.
Yeah, and so this construction, I believe, should have some analog for, say, Ricci flow.
And my second question is, have you guys, so I see there's this problem of when you have say a quadrilateral and then you run a quadrilateral pancake, so to speak. I mean, you start with a very the convex thing, and then you run it, and there's the trouble of two edges, eating the other one, and then you get a triangular shape in the limit.
Yeah, exactly.
Have you thought about, I mean, but the triangles work because of course you cannot lose, an edge. So have you thought of using like an inductive argument, using these triangles as barrier for the
That's a fantastic idea. Yeah. I vaguely remember this, maybe discussing this with Theodore and Giuseppe, but no, we haven't tried. But yeah, that's probably a very good idea. The pancake although it doesn't have an explicit description, we have very good understanding of its
you need asymptotics. Yeah, of course.
So you would need something like that. And in fact, the flying wing examples, we don't even have the right asymptotics yet. You know that after translating, they converge to a grim reaper, but the next lower order term is sort of still not known, which I think might be needed for something like this. But yeah, that's a great idea and probably worth trying.
Any other comments or questions? If it's not the case, let's thank Matt again.
Thank you, Ramiro, and to the other organizers and everyone for coming. Thanks a lot.